Record. Alrighty. So today we're going to talk about model-based RL, finish up our discussion of model-based RL. And then I actually realized I don't have enough time to do the unifying perspectives on RL and IRL. It's going to take 3 lectures and we only have like 4 lectures left. And so unless you want me to breeze through it, which I could do next time, but it's going to be like super fast.
Just show us that helicopter video.
Yeah, we're gonna show you the helicopter video. But there's this framework called control inference, which is a nice way of unifying model-based and model-free RL, inverse RL. I just won't have enough time to get into the details. But if anyone is interested, tell me and we can go through it, but it'll be super fast. Otherwise, my CSE 542 class from last year has a longer description of that material. I think term ends December 6th. I think our poster session we scheduled for December 6th. So you don't have to do anything at final school. And no report this time. Cool. Alrighty, so this is what we kind of outlined last time. It's the anatomy of model-based RL. We started with random shooting and MPC. Then we improved our method to MPPI, and we started doing uncertainty. Today we'll try to cover the last 2 things and then do a bit of inverse RL. So just as the recap, model-based RL, the template is you do data collection, you then learn a model of the world, which is describing how the world transitions from one state to the next. Then you do something like planning, which is trying to use that model as your simulator, try to figure out the right actions. And then you go back and do more data. And so that's the general template of a model-based RL algorithm. And most algorithms try to like change one of these pieces, right? So we started with the V0 algorithm, which uses simple maximum likelihood in order to do model learning. With that learned model, then you do planning with shooting an MPC. And then you kind of go back, do more data collection, everything, right? So the simplest version is we said open loop is bad, but if you do MPC, that's better because you can replan with feedback. But we're still going to do random shooting, which means you're just going to take a bunch of random actions, evaluate how good they are in the model, and then choose the best one. Okay? But it's better than open loop because of the feedback. Now, does anyone remember how we got better than random shooting? How did we improve? Random shooting is just take random actions, roll them forward through your model, see where you got, choose the best one. Yeah.
And we weighted the probability.
That's right.
By their reward.
That's right. So we did this procedure called MPPI, and MPPI says that you're going to sample things forward to the model, but you're going to sample more around things that are higher reward, right? And so you're going to like take trajectories, roll them out forward, reweight actions by their exponential sum of rewards. And so trajectories that have higher return, you're going to like sample around them more. Trajectories that have low return, you sample around them less, right? And so all that MPPI does is it does this loop of, so like in random shooting, you just have a single step where you like sample a bunch of actions, take them forward, choose the best one, execute them. In MPPI, you're going to have this repeated procedure where you sample a bunch of actions, roll them forward, then re-weight those actions according to their exponential reward, and then sample again, go forward, and then repeat this k times till you get a good set of actions, and then you play the first one. Right? And so MPPI is often a bit slower, but often does a lot better. Right? So in your homework, we'll have some MPPI, and essentially it's just trying to do this iterative procedure for planning. Right? And so the nice part is that you're not searching as much for a needle in a haystack. You're making your sampling distribution better and better, and you can show that it's like a low variance distribution for sampling. And so the point is, your model is your simulator. You're still rolling things forward. You're finding a better way to search in your model than just random actions and hoping for the best. Okay, so that was MPPI. And then we talked a little bit about uncertainty, and we said, hey, there's this problem of compounding error in the model. You make a little mistake, you make a bigger mistake, bigger mistake, bigger mistake. Right? And we said that to kind of deal with that, if we can measure the uncertainty of a model, then you can use uncertainty to figure out what to trust and what not to trust. And so we discussed two types of uncertainty. The first is aleatoric, the second is epistemic. To remind us what this means, aleatoric means the inherent uncertainty in your model or in your data collection process. So it's basically saying like, you look at this data, at this point, there's inherently some amount of noise in the data, as in like at this X, there's some variance in the Y's, and that variance is your aleatoric uncertainty. Right? And then epistemic uncertainty is saying that, yeah, I don't have data coverage over all points. And so I don't know exactly which function I'm like which function this data is coming from. And so you have uncertainty over many possible things in the regions where you don't have data, right? So epistemic uncertainty is capturing the noise in the data collection process. And aleatoric is capturing the noise in the data collection process, and epistemic is capturing noise or uncertainty because of lack of data. Right? And so I don't have data here, so I don't know what's happening. And so I always find this graph to be kind of helpful. It's like the places where you don't have data, you still have variance. Places where you do have data, you have variance, but this variance is different from this variance. And a way to think about it is, if I collected infinite amounts of data, this variance doesn't go away, but this variance does. And so you can kind of think of like collecting more data as solving epistemic uncertainty, but not so much solving aleatoric. Or I don't know what solving means, but reducing. Okay, does that make sense? And so if you remember what we were trying to do last time, we kind of wanted to estimate the epistemic uncertainty. We wanted to estimate this guy. And we said one way to estimate this guy is you can estimate the posterior, right? It says that given you have some data, let's say your data was state, action, next state. Like, what is the set of models of this form, which is consistent with this data, right? And so if you remember, we're trying to get this posterior, and a posterior is like by Bayes' rule is p theta, p of d given theta divided by p d given theta times p of theta integral for d theta. Right? Like it's Bayes' rule. And so like one way to think about the posterior is like there's an infinite space of models, and some of them are consistent with your data, some of them are not. And your posterior is trying to say, given that you observe this data, what is the likelihood that a model is consistent with that data? And so if you look at all of these different lines, they're just different samples from your posterior, which means that there are different things that are consistent with the data. You can see that all of them are consistent with the data, but they're different in between. And so you want to get the posterior, and the posterior looks like a prior over parameters. The likelihood function is basically P of S prime given S and A, given your parameters theta. And then you have to like integrate that over all possible models in your denominator. Now, the difficult part of your posterior is the likelihood is easy to, this is your neural net, which takes in S and A and produces a mean and variance over the net. So this is easy to estimate. This is easy, it's some uniform prior. This is the hard part, right? So whenever you have like a denominator, which is an integral, it's just a pain in the ass. So like anytime you can avoid denominators which are integrals, it's good. So the challenge with posterior estimation is always that now you have to integrate over an infinite space of models, and that's very hard to do. And so this whole field there's a field called variational inference, which is trying to avoid this. There's a field called like score-based generative modeling, which is trying to avoid this, right? Like all of them are they try to avoid them in different ways, but they're all trying to avoid modeling the posterior. And so maybe that it's not that relevant to this class, but it's a cool thing to learn. Okay, but we're trying to get the posterior, and we said posterior is hard to do, hard to estimate because of this integral in the denominator. And so there's lots of ways we can approximate it, right? So Bayesian neural networks are one way you can try to approximate the posterior, which is trying to say each weight in your neural network is not just a weight, it's like a mean and a variance, right? And so you can kind of parameterize your whole neural net as like a distribution. And so that gives you a distribution over possible weights. You can try and use techniques to learn that, but that's kind of a pain. What we talked about as an easier approximation is an ensemble, right? So an ensemble means that you're going to say, learn k different models on the same data, Each of those models are not going to be probabilistic. They're not going to be like Bayesian neural nets. They're just going to be regular neural nets. You're just going to have k different models that are trained on the same data or trained on IID samples drawn from the same data. And you're going to try and use the variance of these models as an approximation to your posterior. There's this like nice paper by, his name is Balaji Lakshmi Narayan or something, on how like this is a good approximation to the posterior. But the thought is that if you have an ensemble of models, if you go back to your figure from here, all of those models, they'll start from different initializations that maybe be trained on IID samples of the data. But for things that have lots of data, they will agree. For things that don't have a lot of data, they will not agree. And so the thought is that your ensemble variance kind of captures regions where you don't have data versus regions where you do have data. Now your ensembles don't have to be like point. They don't have to be like S and A. They don't have to be S and A to a point. They can also be S and A to like a distribution over S prime and a variance over S prime. So you can still capture a probability distribution in each of these ensembles. But that is more like aleatoric uncertainty. And like the variance between these is epistemic uncertainty. So an easy way of thinking about it is ensembles differ where there's little to no data, and they're kind of consistent where there's lots of data. And so we're going to try and use ensembles as our approximate posterior and help use that to help with this compounding error problem in model-based stuff. Yeah.
So why are we, if the main thing that we're looking at is the lack of data, why are we going through the hassle of training ensemble models? We can look at, let's say, the first group of data, and then you can get the lower bound of variance.
So it's so your suggestion is density estimation, right? You can like estimate what is the density of the data in any particular region.
Yeah.
Density estimation is a really hard problem. Like so, basically the whole field of generative modeling is trying to do density estimation. But all of the generative models that work are things that don't give you actual densities. Like if you think about a GAN, it doesn't give you a density, it just gives you samples. Or if you think about a diffusion model, it just gives you samples, not densities. And so it's really hard to get densities for a rich enough class of probability distribution. So if I was like if my data was Gaussian, that's easy to do. But if my data is like an arbitrarily complex probability distribution, then it's really hard to fit densities to them. And so that you should do that if you can, but it's hard to. So there's like an easy hack that scales better. But yeah, we should do that if we can. Anything else out there? Okay. So our thought was we now have an ensemble of dynamics models that capture some of our epistemic uncertainty. We're just going to try and learn them with maximum likelihood. There's different ways of doing this. One way of doing this is you can like sample this data IID from the same pool. So you have your replay buffer. And you don't need to send each of them the same data. You just have different IID samples from the data. And there's something called tagging, which one of the groups covered in their presentation. But basically the idea is that if you take different IID samples, things that occur a lot in the data will show up in all the partitions, and things that don't occur a lot in the data won't show up in some of the partitions. And so your models will start to be more different. And you can also have the models be different architectures, different learning rates. You can kind of vary those things. But the point is that you kind of want the models to be consistent on the data and like different outside the data. Sometimes like weird things that happen is like the models are consistent even outside the data, just because the way neural networks extrapolate sometimes is weird. And so lots of the tricks in ensemble world are just trying to get the models to separate outside. Okay. So that is what we did so far, right? That's just a recap. We're going to finish up uncertainty-based models, talk about policy optimization rather than planning, talk a little bit about learning from images, and then jump to inverse error. That's what we're going to do today. Good. So how do we integrate uncertainty into our planning process, right? The first and simplest way to do things is to say that rather than trying to be good under a single model, you try to be good under the expectation of an ensemble of models, right? So you say that, you have an ensemble of different models and you want to be good. If I like take, if I do planning, I want my actions to be good under the expectation of all of those ensembles. And so the idea is that if my ensembles agree, then it's easier to plan through them. If my ensembles don't agree, then it's hard to find actions where it's good across all of the models. And so the idea here is that rather than planning on just a single model, you train K different models, and then you try to choose a set of actions which are good in expectation over all of those models, right? And so the thought is that if I have K different models which are differing outside the data, then I will pick the things that are within the data because that's where I can consistently maximize my reward. And if it's like things where I have high uncertainty, then my ensembles will vary. And so it's hard to get an action that is consistently good across all of them. It's not the best way of doing things, but it's one way of doing it, right? Which is just you just take the expected value of the ensemble. So all you're going to do, right, is you're going to do, let's say you're just doing random shooting. So you're running actions forward through the model. You run actions forward not through one model, you run it forward through K different models. And then instead of picking the best return in a single model, you average the return of every action sequence over all the models and pick the action sequence that has the best average return over all the models. And then you play that. Right. So essentially what you're doing is you're trying to find action sequences that stay in this region, because if they go into this region, the models start to have high variance and it's hard to ensure consistent good performance. Question? Yeah.
So you're saying fix the best average return, is it not possible that there's like trajectories that are high variance, but they somehow happen to be all low or like high reward?
Yeah.
So wouldn't it be better to like
just penalize it? Yeah.
Yeah,
We're gonna do that. We're gonna do that. Yeah. Yeah, you're totally right. Basically, what could happen is that you get like lucky or unlucky in a way that like these things are all high variance, but they're all good. And then you like erroneously take them. So what we'll do next is penalize anything that's low. But this is like arguably the easiest thing to do, which is just all you like. This is the one you're going to implement in your homework. Like all you're going to do is take an ensemble. So let's say you have K different models, like model 1, model 2, model 3. For each of them, you're going to take an SA, get an S prime, SA, get an S prime. Run this forward to get like S capital T, S capital T, S capital T, so on, right? So you roll forward for your model to get many different outcomes. Then you take the sum of rewards for each of these outcomes, right? And then you like average them, right? So how good a particular action sequence is you roll the same action sequence forward through many different models. You take their sum of returns, you average them, and then you try to pick the action sequence that has the highest average reward, right? You're trying to do, in some sense, it's kind of like your expected reward, where there's like stochasticity in your model. That kind of makes sense. The thought is that like if you're here, if you choose to take action sequences here, the models will like vary a lot. And one action sequence may be really good in one model, but really bad in another model. Whereas if you stay in the region where you're not hallucinating, then you potentially get something that's consistent and high value. Okay, but as Sid was saying, there's some likelihood that you like accidentally sample a bunch of things that are different, but all still good. And so the other thing that people do often is they just incorporate pessimism into their estimate, which says that there's like the ensemble variance kind of tells you what regions are known and what regions are not known, right? And so you just take a pessimistic estimate, which means that you're going to maximize the sum of rewards. You're just going to penalize any states that are out of distribution, right? So it's kind of like, you can kind of think of it as pushing down anything that's here, right, in the reward. So in the last objective we talked about, we didn't change the reward. The reward was the reward. And all we did is we said, take the average over K ensembles. Here, what we're saying is we're going to take the ensemble variance and we're just going to like push down the reward in areas where your variance is high. Yeah.
Why do you need why do you need to do this? I thought in Google, like if you if you have you go down a path with high value, that should be fine because once you're done exploring that path, the model's variance should go down.
Yeah, but I guess what sometimes happens, like you're playing a bit of whack-a-mole then, in the sense you're like, there's like many paths you can hallucinate. And if you like are forced to go down every hallucinated path, then you have to like push down each of them one at a time. Whereas I guess that what the other thing is saying is like you've collected some data, do best in data. And then kind of expand from around the data. So like the number of negative paths is huge. And so then it becomes like too much to push them. Okay. So all we're going to do here is we're going to say, do the same expected sum of rewards, but just like push down the states or the states and actions that have high variance, right? Yeah, under your ensemble. So if anything is high variance under your ensemble, that means that it's like less seen. And if it's less seen, you can't trust it. And so you be pessimistic and push things down, right? So if you look up offline model-based RL, like a lot of offline model-based RL methods are things where you can't do what Rico just said. You have a fixed set of data, and you're just trying to find the best policy in that data. And then you can't like whack-a-mole things. And so you have to just be the best in what you know. And so they're saying like, basically, the assumption is that I cannot trust anything that is outside my data. And so anything that is high variance, just push it down. And if you just won't select it. Like this is the same logic as lots of offline reinforcement learning. But it's just like they kill extrapolation. Just do best in data. So are there pitfalls of doing that? Yeah. Yeah, that's true. I guess if you have model architecture, then things that extrapolate, then for instance, in LLMs, I think they're like reasonably good at, they're much better than robotics dynamics models extrapolating. So often when you're doing LLM-based planning, you don't do as much of this like pessimism. But if your dynamics model is not very good, like in like video generative models, then if you plan with them, then it'll like exploit the model as much as it can. And so this is just to prevent model scale.
Are there ways of doing like online model editing? So like the human beings like like immediately have some sort of like
Yeah, I've seen. So in LLM world and whatever, just vision language world, there's a lot of interesting work on model editing. Like you can see hallucinations and edit things one at a time or edit concept stuff. In robotics world, all I've seen is add more data or like change the featureization, but it's like not as well studied. Yeah, so I think it's a possibility. I haven't seen it studied that much for dynamics models. That's a good question. Okay, but the main thing to remember here is basically if there are holes, this is a general principle in lots of RL. If there's holes in your data and you put a really good optimizer at it, it will find the holes and exploit the holes. And so the more you can like either regularize it or be pessimistic around the holes in the data, you'll have less of this exploitation. This is also true in off-policy reinforcement learning, the thing we did last time, right? If you keep running your off-policy reinforcement learning update, if your data doesn't have complete coverage, you'll have holes in the data, and then your Q functions will start to exploit the holes. And so this is not like discussed when you propose the algorithms, because the algorithms are just conceptual, but in practice, if you run too many gradient updates, it'll start to exploit the model, right? This is also often why when you do when we do this maximization, even if you knew the gradient of the reward, you often don't use it because like gradient-based optimizers find holes more easily in your data than sampling-based ones. And so sampling things kind of like tend to smooth over the holes, whereas like a gradient-based optimizer will find the hole and exploit it. And so what's kind of weird is that in lots of model-based RL, you actually use a worse planner to avoid overexploiting your model, which is a little bit strange, but the solution is either to make your model better or to like regularize your planner to not exploit the model. Okay. Yes.
You just mentioned that in general, NDRL, prefer to use like worse planners. Is there like a study that scientists, or is there a paper on study that?
More of a vibe-based comment. Hmm. There's this paper, METRPO, from a few years ago, where they tried, I think, backprop through time and a few of the other gradient-based optimizers. I had a paper last year on diffusion. The keywords has diffusion, model-based offline. Terry, look for those. You will find. Okay, good. So the idea is we, instead of modeling a single model, we model an ensemble, and then we incorporate it into our planning, either by taking the average over our K ensembles, or by explicitly penalizing things that have high variance by being pessimistic, right? So we're trying to avoid poking holes in the data. And if you use some techniques like this, then you can go from the cockroach, which is simpler, to techniques that work a lot better on like higher dimensional problems. So this is like a 24 degree of freedom hand, trying to do like dexterous manipulation, trained in 2 hours in the real world. You can also get it to work for other types of like in-hand manipulation tasks. Right.
Basically, what we're doing, like, we want to remain in the areas of uncertainty, right?
Yep.
Well, like a big part of this is balancing between exploration and exploitation. But what if we want to actually explore the uncertain areas?
Yeah, so I think, yeah, that's a good question. So there's like optimism in the face of uncertainty, which is often what you do for exploration. And then there's pessimism in the face of uncertainty, which is often what you do for offline model-based RL. And so I don't know if I have a good answer for you, but there's like, that's what makes offline to online training kind of hard, because offline to online training, I mean, you have a big corpus of data, you train offline a bunch, and then you start doing online fine-tuning, because you're pessimistic during pre-training, and then you want to be optimistic during fine-tuning. And so what I've seen some people do is basically, because you're off policy, you can always have a pessimistic policy learning procedure. So you're saying always get best in data, but train another exploration policy, which is optimistic. And so you collect data with an optimistic policy, and then the best in class policy you learn is with pessimism. And so it's like you kind of like have an optimistic policy and a pessimistic policy. Optimistic policy collects data. The pessimistic policy says get best in data. And then you can kind of run both of them. I think it kind of works. But in practice, at least what I've seen in most robotic applications is that you run like this thing, and it'll have some degree of optimism. And as Rico was saying, it'll find certain areas that are like overly optimistic and push them down. But yeah, I think if you wanted to balance it properly with exploration, you would have to like figure out how to balance pessimism in the face of uncertainty with optimism in the face of uncertainty. So yeah, it's a good question. So yeah. Okay, so it seems like it works on certain sets of tasks. The only change from the cockroach video I showed you last time to this was the ensemble of models, MPPI, and a little bit of tuning. Okay, so another, like this is our second idea, right? So the first idea, if you remember from last lecture, our first idea to deal with compounding error was to train models on multi-step losses rather than one-step losses. Our second idea was to measure uncertainty in our model and penalize it, right? Our third idea is to kind of rethink of model learning as an imitation learning problem. And we saw compounding error in imitation learning can be used the same technique to deal with compounding error in model-based RL. And so this is the idea. It's an idea called data as demonstrator. But the idea is really simple. It says that in the model, you often have compounding error. Like, let's say this was your data. Like, you'll make a little bit of an error, you'll have another, and so on. It's kind of similar to what we saw in Dagger, right? So in Dagger, you had a little bit of an error, more of an error, more of an error, more of an error. And in Dagger, what we said is like, at these, we're going to run the model. And at these states, we're going to like have a human give us like pi star, right? Human gives us pi star. So the way the Dagger works is you train your model, you run it forward, you take the states you reach, and have a human label the optimal actions. what data as demonstrator says is that in this case, you know where you should be going, right? So you know that at this state, where I should be going next is actually here. And you know at this state, where I should be going is here, right? And so it's saying that like, even like I hallucinated this state, but if I did hallucinate this, like come back to the data as soon as you can, right? And so all that this is saying is like recast model-based RL, kind of like a dagger type problem, and just say like you're gonna create corrective labels which go from x1 hash, which is what you reached, to the correct x2. You go from x2 hash to the correct x3. So if you remember that this CCIL paper we discussed during imitation learning, you're just getting corrective labels that bring you back to the data. And so the thought is that you run your model forward, it'll read some states, right? And then you don't need a human to tell you what the experts are. You just take the next time step in your true data, and you should always come back. So what it does, it creates a funnel that brings you back to the data. And you can kind of think of it as almost like data augmentation, which says like all these things should all map back to here. And all these things should kind of map back to here. And all these things should kind of map back to here. And so the point is that we're not changing our optimizer. We're still doing simple supervised learning. You're just adding more corrective labels to the data so you don't deviate as much. And so the hope is that by adding these corrective labels, you will like converge for the same reason that dagger converges. You're just coming back to the data. So the idea is that we want to, correct model predictions with feedback. So we go here, we come back. If we go here again, we come back. So you never deviate that far from your model. But like a challenge here is like, you can have conflicting labels, right? So let's say you were, let's consider this case where you're generating labels, right? So you went off and you generated a label that brings you back here. But imagine that your true data actually also included this point, and your true data actually wanted you to go here, right? So because you're generating these fake synthetic labels, the synthetic labels might conflict with the true labels, and that's when you run into trouble. And so the point is that what these fake labels are doing is it's trying to tell you to go back your data. But if your true data actually says that from here, you actually want to go somewhere else, then you run into a bit of a problem. Because you're going to have some averaging problems. You're going to go like right in the middle. Your true data is going here, your synthetic labels are going here, your model is going to end up going somewhere here. Yeah.
Brings up another question. What if you have anything that goes between two true label points? Which point should you put that into?
Yeah, that's a good question. What this paper suggests is you just go to the next time step in that trajectory. So like you start from let's say you had a training trajectory. You start from literally the state in the training trajectory, you roll forward through the model with the actions in that trajectory, and you just go to the next time step in that trajectory. And so, like, I guess what you're suggesting is like something like here, right? Or like something like, or if there's like two real data points, and then you have something here, do you send it here or do you send it here?
Yeah.
What they're suggesting here is that you just go to the next time step in that trajectory. So like, let's say you choose a particular trajectory, you roll it forward, you forget about every other trajectory in the world except for that one, and you just go to the next time step in that trajectory. Even if there could have been a better label. So like what could happen though, is like you have two different trajectories, right? And in both cases, you hallucinate to this state. Like what it'll say is one synthetic label will send you here, one synthetic label will send you here, and then you're in trouble. Yeah, so there's issues like that can happen. Okay. So I guess the answer to the question is there's no mechanism right now to deal with that. It'll have both labels in your data set.
So they're saying you should include that label and just go to the next time step.
Go to the next time step, yeah. Because like at this state, you don't actually know which one is the next step, right? Like all you know is your current trajectory. And so if I did data as demonstrated on this trajectory, I'll go here. If I did data as demonstrated on this trajectory, I'll go here. And so I can have both labels in the data set. And then you have averaging.
Well, they didn't say in the paper that, I mean, more the point if you have synthetic labels, like their solution, if I remember correctly, was just like, they have a hacky, the implementation has like a hacky, filter, which is like, we look at the error and we'll just like not use data points that are like straying very far. So just like use a couple first time steps and not anything.
That doesn't address the question though.
Yeah,
right?
it does.
Oh.
It does.
Like that's what they do. Okay,
Yeah.
yeah, thanks. Okay, so that's the third idea. Haven't like, so what's, if you're ever training models, like things that do help is like adding a bit of data augmentation. So when you're like training models forward, what I always find to help is basically if you have some SA S prime data, just like add a bit of noise here. And what it does is it like creates, especially if you're doing position control for robotics, it like creates a bit of like a region around your state where all points to the same thing. And so that often helps a lot with like the prediction horizon of your model, because it like forms a tube around things where you like keep coming back to your data. Okay. So that was kind of our point about uncertainty-based modeling, right? And so we can do better now. We have a better sampling method. We have a better way to deal with compounding error in your models. But the challenge here is that it's still extremely slow, right? It's hard to run in real time. And so if you're running MPPI, especially with a large neural network model, it's still quite slow to run in real time. And so what often is done is you take this process and you amortize it into a policy, right? So you can use your model to do planning, but then you want to like take the result of your planning process and amortize it into a neural network that's going to take in state and produce action. And so the point here is that you will plan in your model, you'll figure out how to like do things. And then you take that decision making and put it into a policy. And a policy is a lot faster to run than a model. Because let's say you had a big model, every time you have to take a decision, you have to run your model case steps forward, you have to run some steps of MPPI, and then you'll make a decision, where the policy just says state in, magic neural net, action out. I guess it depends on the size of your policy, but for reasonable size policies, that'll be faster. And so the idea in this next line of work is to deal with this like real-time policy learning issue or real-time planning issue. And it just says like, let's try to treat our model like a simulator and then just do reinforcement learning in our simulator, right? And out comes a policy and you don't have any planner. You just run your policy, but you just did reinforcement learning inside your simulator, right? So it's saying that like you learn your models same as usual, but rather than doing planning like we've been talking about so far, which means that at any point you're going to imagine the future, pick the best one and act, you're just going to pretend that your model was the simulator and just like learn a policy in the simulator with plain old law, right? And then you'll get a policy, you run the policy, right? And so the idea is that at train time, you collect a bunch of data, learn some models of the world. Those models you can learn with like supervised learning, any of the previous learning algorithms. Then you like use those models to generate data. You put that data into a replay buffer, and then you run SAC or actor critic or policy gradient, like whatever policy optimization algorithm you want, right? But the point is that you pretended these models for your environment or your simulator, and then you just did policy optimization in your simulator, right? So we're doing any sort of off-policy RL method, but doing it with data generated from your model as your simulator. And then the point is that you can use the model to synthesize a lot more data than you got in the real world. But you can get a policy out of it rather than having to do planning at this, right? So you're doing a lot of work at training time. And then at test time, all you do is like you roll out your policy in your environment, you collect more data, you retrain your model or you fine-tune your model, sample more data, do more off-policy RL and repeat. Right? And so this is just what we did in the last like 4 lectures, right? Just SAC, actor critic, any of the like Q learning, any of those methods. All you're going to do is you're just going to generate data from your model. Generate data from your model. Okay? So it's pretending that your model was your real world. You're going to sample a bunch of data. You're going to do policy optimization. Out comes the policy. You'll run the policy in the real world, collect more data, update your model, repeat. Yeah.
Quick question. Why not use PPO?
You can use PPO. Depends how much patience you have. The other thing is PPO is arguably the best optimizer, And so if you have holes in your model, it'll exploit. Okay, does this make sense? It's just saying there's two ways of looking at it. One of them is like replace planning with a policy learning procedure. And then you don't have to do any planning at test time. You just run your policy. So the other way of looking at it is you just do SAC, any off-policy RL method, any actor critic method, you just augment the data with synthetic data generated by your model. Both ways of looking at it are kind of the same. So does this make sense? Kind of. What might be the issue with doing this? Like why is this not just like magic stuff? Yeah.
So we're thinking that all of things we learn are relatively good representation of the world.
Yeah. Okay. And the models may not be. Yeah, models may not be. And so the challenge here is that your models are reasonable around the data, but not that good in other places, right? So if you have like your trajectory, your long horizon models can deviate, as we talked about in the last section. So just pretending it's your simulator will like go down this path, even though this is the path you really want to go down. And so what's the how do we fix that? Or what is the alternative? If I can't use long horizon rollouts for my model, what else can I do? Or I guess I was leading a little bit. But the solution that lots of people have tried and seems to work really well is to initialize from states on your real data and then do like short horizon model rollouts from there. And the logic is that you're like pretty good in the neighborhood of your data. You get worse and worse as you have longer horizon rollouts further from your data. You can prove this. But the point is that you start from different points on your data and then you do short horizon rollouts. Right? And so you have another trajectory, you start from different points in your data, you do short horizon rollouts. And because you're in a model, you can reset to wherever you want. Right? It's like a simulator. You can set it to wherever you want and roll out forward. You don't always have to start from the starting point. You can start from any point on the trajectory and do a short horizon rollout. So it's kind of like a branching, like branching off the real data. And so this often works a lot better. So the point is that you can get long horizon rollouts, they'll just be pretty wrong. Instead, if you start from the real data and do short horizon rollouts, you still get things that go beyond your real data, but they're not so wrong. Okay? And that seems to work a lot better. Read this paper, it's a good paper. It talks about like a good way to choose what the horizon of the rollout should be and what are the trade-offs. Okay, so the scheme now looks like you collect some data, you learn a model, you supervise learning, you generate some data with the short horizon rollouts from your real data, you put them in your replay buffer and do policy optimization, you go and collect more data with your policy, you repeat. Right? So you're just going in this iterative process, data collection, model learning, data generation, RL, repeat. You can do SAC, you can do PPO, you can do whatever it is. But the only difference is we replace planning with policy optimization. Okay. So the trade-off here is that it's more expensive at training time, but it's less expensive at test time, right? So you're doing like much faster inference at test time. So you want to run a model, you want to run a policy really fast. You can run that really fast, but you're going to do way more work at training. Because your policy is not, like the nice part about planning is that it is just local. Like you just have to be good here. Whereas with a policy, it has to be good everywhere, right? Because you can't retrain it. There's some papers that Enrico has been looking at some TDMPC stuff, where TDMPC does something in between, where it starts by doing policy optimization and then refines it with some planning. So it uses policy optimization as a good guess for planning, and then does little bits of refinement around it with planning. But yeah, I would think of it in terms of like how much you do at training time versus how much you do at test time. Okay, does it work? Seems to kind of work. It's an old video from Berkeley on Lego stacking. And if you do like this kind of data hallucination with generated data and policy optimization, they use TRPO here. It seems to learn reasonably quick, like 10 to 15 minutes of training, which is good. And that can run in real time. There's no like slow down here. You're like not doing an expensive planning process. You're just running your policy. Okay. Questions? Yeah.
This is slightly, so you're now running shorter rollouts to train your SAP or like your phone. Does that now mean that either you have to engineer the rewards or you have to take the task, like break it down into subtasks to get around it?
That's a great question. So what you often do is you'll keep the real data around. You will just like do little short horizon rollouts off it, and you don't change the reward. I think what will work really well, and we just had a recent iClear paper which does this, which is do the short horizon rollouts, and if you have something that can truncate the horizon, basically if something can give you signal on which of these short horizon rollouts is good, then it works a lot better.
Did you?
The paper from Tyler and Patrick. So basically what it tries to say is that if you have a value function or something that can tell you which of these short horizon rollouts is good, kind of like reward shaping, then you know which direction to go. So I think that's the thing that you should do. I don't think it's a thing that a lot of people do. Good question. Any other questions? Yeah.
So the policy, the RL policy, do they converge to, I guess, the model that they from SE.SE? So like, if you
I guess when you say convert to the model, like those are different types.
like the best possible policy.
Oh, within the model. I don't know if anyone's done convergence analysis for this particular scheme. There's an older scheme which is related called DINA, and I know that DINA will converge to best in model. But I'm not sure anyone has done analysis with function approximation and like these short horizon rollouts. But I would look at DINA and the related line of work to look at convergence.
These things struggle from stuff like that, having object presidents, right?
Yeah. So I guess I haven't talked about it whether it's images or state, but if you're doing it from images, like in 10, 15 steps, you start losing object permanence and you start getting blurry and so on. So yeah, I think it's getting better every week, every month. But I wouldn't say it's perfect at like retaining physics for object permanence. Okay. And then the last bit of model-based RL we're going to think about is how do we do this with images? To Kunal's question just now. So if we want to go from low dimensional states, so like these kinds of domains where you like know the joint angles or you know where the objects are, to like Minecraft or robot or whatever, DeepMind Lab or robot navigating around the world or some like web agent operating from high dimensional pixel observation. How do we do that, right? So the first idea is that you can just try and predict. We've been talking about predicting P of S prime given SA models, right? You can just make these images. Okay? So you can say, take in the current image and action, predict the next image. So just like, just do reconstruction. You take in current image, action, reconstruct the next image. And then you start seeing results like this. So that is at the top, you have ground truth. And then you have like predictions here at the bottom. They're like not very good. Even for like these tiny short horizon rollouts, you can see that they start to get blurry pretty quickly. And they don't really push objects. They like go through objects a lot. They like lose object permanence through occlusion. Generally, it's never that good of an idea to just do one-step reconstruction for images. It doesn't work very well. So I think even now, long horizon prediction in video space is pretty hard. And so predicting pixels very, very far into the future is still a challenging problem. Right. And so this is like models that directly take in images and action and predict next images. And so the thing that has worked relatively well is these latent space models. And the idea of a latent space model is that your normal MDP looks something like this. State, action, next state, action, next state. Something that is more like a POMDP looks something like this, where you have state, action, and an observation. An observation is kind of like, let's say if state was like where your robot joints were, where the objects were. You can't see it. All you can see is an image, right? And these latent space models essentially try to solve this POMDP. And so the idea is that you can try and learn a mapping from an observation or a history of observations into a latent space or a distribution in latent space, which is far more compact, and then try to learn dynamics in that latent space. So earlier we were trying to learn P of S prime given S and A. Now what we're going to try and do is we're going to try and go from some observation to some Z, and then you're going to try and learn like how to transition in latent space. And so the idea behind most of these latent space models is that we're going to try to go from an observation to a latent space, predict dynamics for many steps in my latent space, and then come back out to my observations. And so they're trying to solve this kind of MDP. I'm not going to go too far into the details, but the general idea is that you're going to try and learn a latent encoder to infer your latent state, let's call it SC, given a history of observations. They're going to say, I have a history of observations, O1 to OT. I encode that to get some latent state ST. Then I try to learn a latent dynamics model. So something that goes from ST and AT to ST plus 1, right? And then I try to learn a decoder, which goes from ST plus 1 to OT plus 1. And then I also have a predictor that goes from my next state to my reward. And so essentially the idea in most of these models is that you try and combine these objectives, one of them which is trying to encode, another one which is trying to predict forward dynamics, another one which is trying to do reconstruction, another one that's trying to do reward prediction, right? So a way to think about it is you have OT going to ST, ST going to ST plus 1, this predicting RT plus 1 and OT plus 1. And so you have gradients flowing back this way, you have gradients flowing back this way, and you'll have some regularization terms of. Right? And so you can kind of think of a latent space as something that is sufficient to be predictive of the next latent, the next reward, and the next observation. And what more recent methods have tried to do is try to like get rid of this observation reconstruction and just say you want a latent space that predicts the next latent and the next reward. Right? So that's what CDMPC and other papers will do. But they try to say a sufficient encoding of my observation is something that is predictive of my future reward. And to be predictive of my future reward, I need to be predictive of my future latent state and my current reward. And so the idea behind a lot of these methods is just go map into latent space. You don't have to ever reconstruct images. You just need to be predictive of future. Okay. Does that make sense? So most of the think of the latent space images as just like our latent space models is going from observation to latent. Dynamics in latent, not in observation space. You're not going back to images every time. You're just in latent space, and then you come back to images if you want, or you can just predict rewards. And so once you have this kind of model, you can then do planning in your model, right? So you just have something that goes from OT to ST. You can just run a bunch of like forward rollouts in your ST, just do planning, same as usual, pick the best one, execute it, and then repeat, right? And so all of the stuff we did earlier can also apply here. Just do it in latent space, right? So you're avoiding image prediction. You're never doing image prediction because your rewards are all in your latent space. And you're doing a lot better than image prediction because you don't have to come back down to images. Like if you look at the videos from earlier, like you never have to deal with this kind of blurry images. The hope is that if you can just predict forward in latent space, you can just plan in the latent space, you can get policies in the latent space. You don't have to worry about dealing with policies from those future blurry images. Does that make sense? Question? Yeah.
So now you need the reward.
Yeah.
It's sounding more like doing model where you if I had like a new reward, now I have to retrain.
Yeah, that's a good point. Yeah, so that's why I think model-free RL and model-based RL are not that different. They're very related in that like one of them is predicting rewards in the future, one of them is predicting states in the future, but they're kind of similar. You're right that the versions which pass in gradients from rewards become specialized to a particular problem. And so then it's hard to transfer to new problems. What they'll often do though is like they'll like pass in a task descriptor as part of the state, and then they'll predict many different rewards and that kind of stuff. But yeah, it does become specialized to a particular problem.
The way to get around this is to have a task descriptive part of the state
Yeah.
as the thing that is being predicted.
Yeah.
It's almost like you're,
You're just expanding your state space.
or yeah, so I was thinking about it like you're now bringing back the structure that you had. Yeah. But okay.
So, that's the general idea. Just think of it as you're trying to learn and think of it as your observation goes to latent, latent goes to next latent with an action. Next latent can go back to observation at training time and a reward. And then at planning time, you throw away the decoder. You don't need the decoder. You just plan forward in your latent space and pick, like, you can learn policies in it. You can do planning in it. You never have to come back out to image space. And so the hope is that it scales better to images than just like pixel prediction. Allows you to predict longer horizons in the future because you don't have to keep coming back to images and building blurriness. You can keep going in the latent space. And so it tends to do a lot better.
So to be clear, you have a decoder that you're using at training time, like
Mhm.
that propagating through it from the observations at every time.
So there's a version called Dreamer, and what Dreamer does is it has this decoder. The decoder goes from observation back to state, from state back to observation. But if you throw it away at test time, all you need at test time is a policy or a planner in latent space. What TDMPC does is it says, we're not even going to have this decoder. We're just going to have a reward decoder. We're just going to have something that predicts reward. And then the idea is like, all that you need to retain in your latent space is things that are predictive of reward.
So how do you train it then?
You have rewards. You're given rewards at training time. And so you train it, like the way you train it is like observation goes to latent, latent goes to next latent. And then you have like a reward at the next time step, and that gradient goes back. So like you know the true reward. So there are true in the next time step, so you collected a trajectory, right? And so you can like propagate the gradient from the next reward. Whereas what Dreamer does is it adds this like reconstruction step, and then it also passes the gradient from there. Right. So the difference between Dreamer and TDMPC in a way is that Dreamer is going to like pass gradients to the reconstruction part, and TDMPC is going to avoid this. The nice part about Dreamer is there's a lot more supervision, but you're like trying to reconstruct everything. So you have dynamic scenes. It's like really hard to deal with reconstructing dynamic scenes. Whereas TDMPC is only predicting things that are relevant for reward. And so then you're like, as Sid was saying, it's almost like a model-free method. You're discarding things that are irrelevant to your reward because they're not even in your loss. But in both methods, once you get your latent space, you kind of throw away your decoder and you just generate policies in your latent space. So this is a video I showed last time, I think, of Dreamer doing super well on Minecraft. And it does stuff that is supposed to be good. But this is what I like more. It does stuff with robots. You can learn to walk around in an hour or so interaction. You can learn some manipulation tasks. They have like a cool little robot here, which is like a little rolly robot that they trained with model-based startup. Let's see. Yeah, they trained this little rolly robot which rolls around and gets to places. So yeah, point being, it's super efficient, learning from images in the real world. So it does kind of work, but it's still, I mean, these are not near home. So I think there's still quite a gap from here to like a deployable system. Okay. So that was learning models from images. Questions? Okay. So a little bit of perspective before we go to IRL. So model-based IRL, I think, is important. It's practical for these reasons that I mentioned last. We talked about how it's not so simple and we shouldn't do it all the time. But the one I find most compelling is the fact that it should be able to transfer across problems. Like if you can model the dynamics and the objectives separately, you should be able to like swap out your objective and still reuse the dynamics of the world Whereas if I just did policy gradient, I know how to do this thing. I don't know how to do this other thing, right? And so to me, it feels like a great way to do transfer. But I don't think we figured out, not a lot of model-based RL papers try to do transfer. And so still a lot of room for exploration. And a perspective I find useful is to think about how models and Q functions are related. So they're similar in many ways, right? They're both off policy. Both of them are modeling something about the future. Q functions are modeling what is the expected sum of rewards in the future. So Q functions are modeling not states, but rewards, and not time step by time step, but cumulative. Right? So those are the two differences. You're modeling agnostic, like reward task agnostic state, and you're modeling it time step by time step in a model. Whereas a Q function mushes it together across all the time steps and models a particular reward. Now there's these methods called successor feature methods that get in between, but they're similar in that they're modeling the future. I think policies are different because policies say you're at this state, this is where you want to get to, how should I act? So Q functions and models are causal, they go forward, and policies are anti-causal. They say like, I want to accomplish this, how do I do it? Right? So policies go from the future outcomes to a current action. Q functions and models go from a current state to future outcomes. Right? And I think they're different though, in the fact that models do one step, Q functions do cumulative, you model state versus model return. You can evaluate arbitrary policies. You can stick in any policy you want into a model, but for a Q function, it's for a particular policy pi. So if you look at a bunch of the work from my group recently, they've been trying to like bridge these gaps. And so like try to get models to look more like Q functions, but still be transferable. The problem with models is that they still have compounding error. The problem with Q functions is that they're specific to a particular reward, particular policy. And so you can try and find ways to like bridge the gap so you avoid compounding error while still being able to like evaluate arbitrary policies and arbitrary rewards. Okay, that's just some perspective. Cool.
There only work, but is it cheaper to translate like an image into some functional model and unrealize it, but already something planned in there?
Yeah. We've actually been doing a bunch of work on that. It's like, I guess it's often called real to sim to real. Like you're trying to go from an image to a simulator to futures and come back. It's like, I guess, a special class of models where you have physics. The challenge is often like getting, like Max does a bunch of that, Max Clem. But the challenge is often like reconstructing the world in accurate ways is hard. And it might be, and because if your models are non-differentiable, like a simulator, it's hard. You often have to have a zeroth order optimizer, which is expensive, and or you have to have some like 3D reconstruction pipeline and a system ID pipeline, and that is expensive. Whereas an end-to-end model may not have that problem. So I think it's a great idea. I think it's like still unclear if it works.
And that's sort of built like propagate rates to like
How do you figure out the parameters of your algorithm? It's like you have to go from, so there's the geometry part of it, which is like what are the shapes in the world? There's the kinematics, which is like how are things connected to each other? Like what are joints, what are doors, what are cabinets, what are handles? And then there's physics, which is saying like what are the friction properties, masses, and so on. And you kind of want to set all of those from the real world, because you want all of those to be realistic. And so what I often find, I feel like geometry is the one that we know the most about. The other ones are a bit harder to get right. But I think it's super promising. Okay. Okay. We can start thinking about inverse RL. Should we go there? Do you want a break? Okay. We'll do some inverse RL. So, we've been talking about RL for the last 6 weeks or 7 weeks. And we've always been talking about maximizing the sum of rewards. And we've said, okay, rewards are going to show up. Rewards are great, but they are part of the problem definition. But for any problem that you actually care about, rewards don't really exist. They're like completely made up, right? And so we studied a bunch of algorithms to solve this problem. But like, what is the problem? In the sense, in most problems of real interest, like in a robot in the world, what is the reward? And it's not given to you. You often have to find a way to specify it. And so all these methods operate under the assumption that the reward is known, but it's usually not known, and we have to find a way to generate it. And so what most RL algorithms assume is that reward, shows up magically from the environment. That's true in Atari games. It's not true in most other things. And so in most cases, you're manually specifying them. So for instance, in some robotic settings, you have like motion capture markers. You like specify some detailed reward based on those motion capture markers. Or you'll detect where objects are and say this object needs to go here, and like you hand design some reward function. This is an example from Dota from OpenAI a few years ago. And that the reward function is all of these different terms with all of these different coefficients that were like tuned by hand for one problem, right? The same for locomotion, the same for manipulation. Like often reward design is just a huge fail. And when you're doing it manually, that becomes tedious for every single problem, right? And so what IRL tries to ask is, can we find ways to infer reward in a less manual way? Right? So it's saying, we're not going to get reward magically. We have to find a way to specify it. There's a manual way of doing it. Can we do it automatically? Okay, so that's the basic premise. And rewards are ill-defined. Like what do rewards mean? The basic premise of inverse RL is that you're going to be provided some set of expert demonstrations, right? So you're going to be provided some demonstrations, some traces of expert behavior, something that shows what the desired behavior is. So you're going to get a set of states and actions, sometimes only states, which demonstrate expert behavior or close to expert behavior. And what inverse RL is then going to try and do is going to use those demonstrations of expert behavior, some interaction with the environment, try and find a reward R. And then the hope is that we can then use the reward R in new scenarios. Right? So we can try and use the reward R in settings beyond the ones that were demonstrated. Right? So if I was just in the states that were demonstrated, then I don't need it. But if I'm in some new states, the hope is that reward R can be used to learn a policy that generalizes more than just the expert demos that we built. And so the idea of inverse RL, you collect a bunch of expert data, you infer what the rewards were that explain the optimal behavior or explain the demonstrated behavior. And so once you get the reward, you then need to optimize a policy which generalizes more than just these expert demos. And so the reason it's called inverse RL is because RL goes from reward to trajectory. Inverse RL goes from trajectory to reward. Okay? So RL takes in a trajectory, takes in a reward, optimizes a bunch of stuff, gives you an optimal policy. Optimal policy gives you expert traces, gives you optimal behavior. What inverse RL says, you're given the expert behavior, try to find the reward that explains this expert behavior. Right? So that's why it's inverse. Okay, so we already talked about learning from demonstrations, right? This is the second lecture of the course. So we talked about behavior cloning. It already does learning from demonstrations. Why do I need this inverse RL thing? So the difference, let me make clear, is behavior cloning tries to take in a set of expert demos and just tries to learn a mapping from state to action, right? So BC tries to say state to action using a policy. IRL tries to say set of demonstrations to a reward. Reward can then be used with RL to get a policy. Okay, that's the difference. Why would you ever do this? We haven't talked about how to do it. The one like think of it as like one of them is got an intermediate step of figuring out what the reward is, and then you have to stick it back through RL. Yeah.
Something to do with co-leadership, like you've seen like a lot of these states, and you can sort of share information, sort of like how we did with Q function almost. Yeah. So you're sharing information, and so even if you go to state that you didn't see, like if you were doing imitation learning, you go slightly out of distribution, you're not seeing that state. But with IRL, you could have an idea of like what the reward for this kind of state.
Yeah. So I guess extrapolating from Sid's point, the first reason is that behavior cloning has covariate shift. RL would not have covariate shift. So if you do IRL plus RL, you don't have covariate shift in the same way that behavior cloning does. The second is that reward functions are often more compact descriptions of behavior than policies. And so a reward function potentially generalizes better than a policy, right? So like imagine a policy which is trying to like navigate some obstacles and get somewhere versus a reward function which is just like get the obstacle, get the goal, or pick up the object. Like pick up the object generalizes a lot better than like something that tells you an exact path. Right? And so the thought is that reward functions generalize better than policy. And doing RL helps avoid compounding error or covariance shift. So the whole premise of if you're doing inverse RL and it doesn't generalize, there's no point of inverse RL. Just do behavior cloning, right? So the whole premise of inverse RL is that behavior cloning learns policies, inverse RL learns reward. You need rewards because you want to generalize to new settings. And the thought is that rewards are simpler than policies, so rewards will generalize better than policies. And so we really care about generalization across states, right? So if you have, let's say you got demonstrations of picking up in these 4 different places. If I place a block here, I should still be able to solve it. And policies often struggle to generalize and rewards are often simpler. And the same across dynamics, like if you have like 4 different robots, if I like showed it how to pick up objects here, I should also be able to know how to pick up objects here. And so the thought is that imitation learning or learning from demos really needs to generalize. And rewards will generalize better than policies. That's the claim. I don't think we have that much evidence that this is true, but it's just that's the like premise behind inverse RL. I think it's yet to be demonstrated that they do generalize that much better. But the point is that like there's some simple things that hold, right? So like imagine that you had k different policies, so each of them have different dynamics. Right? P1, P2, P3, but all of them might have the same reward. Like in all of them, you need to pick up a box and pick it up. Right? So a reward can transfer across dynamics when a policy can't. If you learn a policy on this, doesn't work here, right? But a reward can transfer across. Right? So you often want to do IRL because like a reward is simpler and it's easy to transfer across dynamics. Right? So if you're ever doing IRL, try to think about it from the perspective of transfer. If not, behavior cloning is a really strong baseline. Okay. So the point here is that rewards often don't involve dynamics or don't entangle dynamics. Policies and Q functions and value functions often do. And so if I want to learn from demonstrations, like it makes sense for me to like want to extract a reward. Right? And the second point is that if you're trying to learn things with RL, it kind of avoids compounding error because you're sampling under your policy, not under your expert data distribution. The same thing we covered in lecture. It's like the difference between reverse scale and forward scale. So you can kind of think of the process of extracting a reward and doing RL as like reverse scale because you're sampling under your policy. You can kind of think of behavior cloning as forward scale because you're sampling under your expert, right? And so here in behavior cloning, you're training under your expert, evaluating under your policy. In RL, you're training under your policy, you're evaluating under your policy. And so this avoids compounding error, and this has compounding error. Right? So if you're ever thinking about why use inverse RL, like these are the typical reasons. Because it's going to be a little painful. And so, you know, when you're in the hell of inverse reinforcement learning, remember this motivation and it'll motivate you. Okay, so how do we learn rewards from human data? You're going to have some set of data that you get from an expert, some set of traces. You then want to find what reward can best explain that data, right? So that's the point of inverse RL. And so we need to make some assumptions about the expert provided data. We're going to make the assumption that the expert provided data is close to optimal, right? So we're going to say that the expert provided data is noisily optimal. Think about it like if I just had random data, then how do I extract a reward function? It could be under anything, right? And so I'm going to assume that the human is a rational agent or an approximately rational agent. And I'm going to assume that the trajectories that I get are coming from some approximately rational agent. By rational agent, I mean something that's optimizing a utility. And so you're going to assume that the demonstrations are noisily optimal. Otherwise, it's an ill-defined problem. Yes. So I'm going to get expert demonstrations, I need to extract a reward. And so, skip to this. The problem statement here is that in reinforcement learning, you know the state and action, you know the transition dynamics you can sample from, you know the reward, but you don't know the expert policy and you don't have traces from the expert, right? You're given state, action, dynamics, reward, you need to optimize it. In inverse RL, you know the state and action, you don't know the transition dynamics, but you can sample from it. You don't know the expert policy, but you also don't know the reward, but you do know traces from the expert, right? So the difference between these is mainly this guy and this guy. Right? One of them reward is known, one of them reward is unknown, and one of them expert traces are unknown, and the other one expert traces are unknown. And what you're trying to do is you're trying to find a reward function R that best explains the demonstrator behavior under the assumption of noisy optimality. Right? When I say noisy optimality, I mean close to optimal. Okay, so the process is going to be take some data, extract a reward function, and the new problem, I'm just going to redo reinforcement learning. I'm going to get a policy. So inverse RL will go from data to reward, and you'll do forward RL to go from reward to policy. Some inverse RL procedures will give you reward and policy together, but not all. Okay, does it actually work? This is some stuff from Stanford from a few years ago, and they not a few years ago, it's like 15 years ago. Yeah. They did parking lot navigation. So they had some demonstrations of a car navigating a parking lot. They inverse RL on it and show that you can navigate in new settings. You can also apply to locomotion type things. So here they had like this again from early 2000s. But they're trying to like navigate through this like terrain with lots of bumps. They have a few demonstrations, try to get a reward. A more recent example, I don't know if I have it here, is the one on the first slide, where they actually use it at large scale on Google Maps. And so they look at like how people navigate it on Google Maps, and they use that to like optimize for cost functions on Google Maps, to like characterize human preferences and so on. Okay, so yes, sir.
Don't people usually follow Google Maps? Doesn't it like create a concord of like whatever Google Maps is?
It does create
reading
a bit
our
of-
stuff.
That's a good one. That's a good point. Yeah, I agree. Okay, so what makes inverse RL hard? Firstly, inverse RL is inherently underspecified. There might be many reward functions that explain a particular behavior, right? So like, for instance, I picked up this pen. I could either have the reward function be pick up the pen, or I could have the reward function be navigate to this point and close your gripper and then move up. They both explain the data, but one of them is better than the other. So it's like an inherently ambiguous problem. Both your reward and your optimal policy are unknown. You just have traces from your expert. Often you don't know the transition dynamics, and it's hard to know when the reward function is optimal without like seeing how it plays out in the world. And so a lot of inverse RL is going to require sampling in the environment and exploration and RL. Most inverse RL algorithms have an RL loop inside it. So inverse RL is often harder than RL because it has RL as a subroutine. And you often don't know how to compare things. Like if you have two different trajectories, or if you have two different rewards, you don't know how to compare which one is better. And so those things kind of make the inverse RL problem. That's the basic problem formulation. Let's go through the rest of it next time. But cool. And homework 2 should be already due, right? If anyone has problems, let me know. And homework 3 should be out tonight.